little bit of the background of these people who are there. कहाँ कितने I think I can kind of see आप में से कितने teachers कितने हैं और students कितने हैं.
सर गुड मॉर्निंग, मैं एस एस आलम बोल रहा हूँ.
हाँ जी.
सर यहाँ पे करीब इस वक्त 10 टीचर्स हैं और बाकी स्टूडेंट.
अच्छा. And the students are what level? The graduate or undergraduate or postgraduate?
सर इसका मिक्सचर सॉर्ट ऑफ.
हाँ जी.
अंडर ग्रेजुएट भी है और पोस्ट ग्रेजुएट भी है और रिसर्च स्कॉलर्स भी.
मास्टर पीएचडी.
यस, मास्टर्स एंड पीएचडी वाले भी हैं.
अच्छा. और सीएफटी की बैकग्राउंड कितने लोगों की सीएफटी की बैकग्राउंड है?
तो टीचर में तो है बैकग्राउंड और कुछ स्टूडेंट्स में भी है. करीब 15% स्टूडेंट्स में है और 30% टीचर्स में कह सकते हैं.
So there is a total of how many people? 35 people in the class?
Yes, sir, 35 people and they are also coming now because of Sunday जरा सा relax हो गए तो लोग आ जाएंगे.
ठीक है.
तो सर मैं आपका एक ब्रीफ इंट्रोडक्शन हो जाए सर, उसके बाद अब आप शुरू करें.
ठीक है.
तो ये फैजान साहब करेंगे आपका थोड़ा सा, हमारे यहाँ प्रोफेसर है.
ज्यादा छोटा सा इंट्रोडक्शन करना, बहुत लंबा मत कर देना. I'd rather talk to the students.
The one you sent was quite long. I have cut it short to half a page.
Yeah, one paragraph would be plenty.
Yeah, and I think I cannot go below that.
Okay.
Yeah. Dr. Akshai Kumar Runchal is the founder and president of Analytic and Computational Research Incorporation and is an acknowledged expert in computational fluid dynamics and numerical simulation of flow, heat and mass transport process in engineering and environmental sciences. In late 1960s, Dr. Runchal was a key member of a core group of 3 persons working under the guidance of Dr. D.B. Spalding. We are aware of him, at Imperial College London, that developed the so-called Imperial College finite volume method for CFD applications. Dr. Runchal received his PhD in fluid mechanics and transfer processes from Imperial College London, UK in 1969 under the direction of Professor D.B. Spalding, and a Bachelor of Engineering with honors from Punjab Engineering College, Chandigarh, India in 1964. He is contributor to over 200 technical publications and numerous books. He is the principal author of Answer, Overflow, Tidal, and RAGM CFD software tools, which can deal with a broad spectrum of problems in fluid dynamics, heat and mass transport, combustion, and environmental pollution. Dr. Runchal has provided services to over 200 clients on an international basis. His clients have included major corporations and research organizations in many countries. He has worked extensively with leading research organizations such as Sandia National Lab, Oak Ridge National Lab, Idaho National Engineering Lab, National Academy of Sciences, and corporations such as Exxon, Chevron, Sohio, Shell, Arco, Aramco, BP, Total, Bechtel, Flower, Dames and Moore, Woodward, Cyclade, and the list goes on. So over here to you, Dr. Runchal. I don't want to come in between you and the audience anymore. All right.
Thank you. I think my brief introduction is that I'm one of those fellows who was lucky enough to find something that was close to my heart back in 60s, and that was computational, or that was fluid dynamics. And unlike many of you who perhaps will not stick to engineering or stick to what you're learning today, less than 50% of the engineers go on to do engineering, as you know. But I have done nothing but computational fluid dynamics and transport processes. So I really enjoy it, and I think it will come through, and I hope there are at least 1 or 2 out of you who would take this as a profession and stick to it. Okay. Is there a little bit of echo, or can you hear my voice all right?
Yes. Volume.
थोड़ी एको है या मुझे लग रहा है जैसे एको है. आपको ठीक आ रही है आवाज? हाँ जी.
कंफर्टेबल बोलिए ना.
Okay. People at the back can understand me? Okay. All right. Okay. So let's start. We are a little late, but let's start. I'm going to talk generally about CFD, and originally when I know you're learning something very specific for the last 2 days. So I wanted to give you a little bit of the past of CFD, a little bit of the present, and a little bit of the future. Okay, how did it go on?
F5.
F5 चलेगा?
Yes, sir.
अच्छा, क्योंकि मैं वो एंटर कर रहा हूँ तो एंटर से नहीं जा रहा, डाउन से नहीं जा रहा. अच्छा.
Next.
नहीं, विकल्प.
Either a slide show you.
हाँ, this is the slide. हाँ, it's frozen on my. Is this a new slide for you?
Yes, sir. Yes.
Are you seeing a slide that says summary of talk?
Yes, sir. Yes, sir. Yes, sir.
Okay. So I'm going to try and cover 4 things quickly, some in bit of detail and some little more, concisely. So what is CFD? And then the next question is, how did we get to where we are today, and what can we do with it? And then, of course, finally, very briefly, I'll talk about where we are going next. I'm sorry, you bought the. Okay, hold on. I think. Let's see if this one would work better. मेरा ये फ्री हो रहा है, फ्रोजन हो रहा है यहाँ पे. Did you? No.
Either you can use a slideshow or full screen.
हाँ जी. अब आगे next slide.
Yes, sir. Fluids and solids.
अच्छा. Okay, so basically the physical world is roughly divided into solids and fluids. You all know that. And just briefly, solids retain their shape independent of their location, as long as there is no external force, right? So if you have a cell phone in your pocket, it has a very definite shape. It stays like a cell phone. You take it out, you put it on the table, it's still like a cell phone. Now, fluid, on the other hand, is something, it's a form of material that conforms to the boundaries. In other words, if you put the fluid in a glass, if you take some water, put it in the glass, it will take the shape of the glass. You put it in a tube, it will take the shape of the tube. Except that for a liquid, there will be a free surface. And it may or may not fill the glass, depending on how much water you have. A gas, on the other hand, completely fills the total containment vessel, right? So these are the very basic things that you learned, okay? So let's go to the next one now. So in reality, though, when you really start to look at it, there are no solids. For example, iron is a solid, typically. Our buildings contain a lot of iron. They are all solid bars or something. But you look at the core of the earth, and iron is a liquid there. Okay, it's not a solid anymore. It's a fluid. So if you take any solid, you heat it up, or you put a lot of pressure on it, it will melt, or it will begin to flow, it will begin to deform, and then we call that a plastic state of things, when the solids begin to form, solids begin to flow. Okay? So there is a continuous transition of matter between solid, liquid, and gaseous phases. And so we have solids in the form of plastics that flow, and that can be made to flow like a liquid. There are intermediate forms of matter, such as a triple point. There is no specific phase. All phases are present simultaneously. And then finally, if you keep on heating it and you keep on raising the temperature, at some stage, a fluid begins to dissociate, a gas begins to dissociate and form what is called a plasma, which is an ionized gas. Okay? So, in reality, any solid is a fluid which is frozen. Now, what is it that CFD can do? So, CFD predicts the behavior of fluids, including plastics and deforming solids. Okay? And today you will hear a lot about multiphysics CFD. And what it means basically is the typical old design of implement of interpretation of CFD was that it was basically fluid dynamics, little bit of heat transfer, maybe a little bit of mass transfer thrown in. But today you find electromagnetism, and you find there are a lot of disciplines depending on the application. For example, if you're applying CFD to deep underground, you will have the geology come into the picture. Okay? And if you're applying it out in outer space, you will have astrophysics come into the picture. So those are all what are called multiphysics applications. And that's what they mean by multiphysics today. Now, why do we do this? We do this because it has become very clear that to understand our physical world, we need CFD. Man inhabits fluids. We live with water all around us. We are inside a cocoon of atmosphere, which is air, which is a fluid. We have oceans, we have rivers, we have rain. So fluid, without fluid, there'll be no life. And also without fluid, there'll be no human. Because a human being is 2/3 liquid or gas, and the other 1/3 is basically plastic. Okay, so there's no part of human body which is really solid in that sense. We do have bones, but even bones grow with time, bones decay with time, bones can break, bones can melt, all kind of things can happen. So CFD applications span the human existence, industry, environment, human body, biosphere. So CFD tools are very critical to a number of fields: aerospace, energy, transport, national security, disaster environmental management, engineering design, health, life sciences, etc., etc. Okay. So there is no human activity today which is not touched by CFD. It's very pervasive. It's not possible to design an aircraft. It's not possible to design a computer system or electronics without CFD today. It's not possible to manage and understand the environment. And so I could go on and on, but basically, let me take 4 specific application areas and show you what CFD has been used for in those. Let's take the aerospace technology. This is actually one of the key areas in which CFD was first developed, was for aerospace technology. And so it played a very crucial role in many aerospace applications. Okay, every single major aerospace project since the 1960s has been dependent upon the CFD. Today, the premier design of aircraft, premier design an engine, of a rocket, of anything that flies is first done on the computer and only then tested in a wind tunnel. So perhaps the most valuable case was for Boeing 737. The nacelle was redesigned completely using CFD. Boeing 737 would have become obsolete in the 1980s had it not been redesigned, and that redesign was done by CFD, and that's why 737 in various forms is still flying today. India, on the other hand, unfortunately, we still do not have our own jet engine as of today, and part of that, there were multiple reasons. For the last 30 years, we've been trying to design a aerospace engine, a jet engine, and we not succeeded. And part of the reason was that we did not integrate CFD into the design cycle as is the practice today. So testing became very spotty and it never led to the right results. Let's look at the environment, the other very important field today. Let me take one particular example from nuclear industry. Nuclear industry generates nuclear waste. Now this waste can stay toxic for 100,000 years or maybe more, okay? You have to isolate it from human surroundings for such a long time. Now put it in perspective, there is no written history of human beings which is reliable for more than 3,000 to 4,000 years, and even that has questions. 100,000 years, we don't even know what the state of human society was. We're perhaps still living in caves, or I think the agricultural age had just begun. And yet we are asked to design something that will last for 100,000 years. We don't even know, there is no structure that we have designed which has lasted for more than 1,000, 2,000 years. Okay, they all failed. How can you do it? The only way to do it is through CFD. To study the problem in all its ifs and buts, and then find out what would be the best option, and then put in enough safety factors and go with that. That's just one example. Other example is today, lot of damage has occurred because of tsunamis, for example. Now, there's a lot of effort today, and it is possible today, if the governments were just to turn their mind to it, to predict what a tsunami will do, to design your coastline in such a manner, design your residences in such a manner, design your industry in such a manner that any tsunami will not impact them. Okay? So there are many other examples I could give, but I'll show you some practical examples down the line. Then the next cutting edge that is coming in CFD is the health, pharmaceutical, and life sciences. The human body, before long, there'll be no part of the body which cannot be replaced. Not even the brain. Even the brain is being, parts of the brain are already being replaced. Okay? And all that is being done with CFD in one form or another. For example, testing of drugs. How fast does a drug diffuse in the brain? How fast that drug goes into the blood? How do we make an artificial heart? How do we do a dialysis? Each single one of these involves CFD today. Let's look at national security. Security today, Army is going very high tech. You've heard of drones. People control drones hitting thousands of miles away. But more than that, the best example is that under the Test Ban Treaty, nobody can actually test a nuclear weapon by exploding it. So the only way to test a nuclear weapon is by simulating it. And US has a program called ACRI, Advanced Simulation and Computing, under which tools are being designed which can model a fire and explosion, the impact of a shock wave, the deformation of solids into plastics and liquids because of the nuclear explosion. Okay? So all these is just some examples, and then virtual reality is coming in, and I'll talk a little bit about it later. So that was what CFD is. I now move to the second part of how did we get here. I want to give you a little bit of history. Most of you are very young. I presume that the average age is perhaps about somewhere between 25 and 30. So CFD started 50 years ago. One generation ago for you, 2 generations, some of you. So I grew up in a remote place in Himalayas, in Dharamshala, or specifically McLeodganj. I guess all the young people have heard about it. In my days, nobody had heard about it. When my mother got married and she said she was going to Dharamshala, then all her in-laws and other friends who had come, they said, don't worry about it, eventually you'll have a house. Okay? So I never dreamt that I would be part of a development of CFD, and and I didn't know that Dharamshala would become on the international map. But that's what happened. I went to Imperial College. I took part. I was lucky to be at the right time, at the right place, and we helped develop CFD. And Dharamshala, then Dalai Lama came, was exiled in Dharamshala, and Dharamshala became very well known on international map and is now a hot political spot between India, China, and US. So life has coincidences, and I am indeed a lucky man. This is where I live half the time, and this is my home. I don't know if you can see my cursor. Can you see my cursor there?
Yes.
Okay, my home is right there, and this is the moon I grew up every day. This is the moon peak, the mountain I grew up every day, which used to be always white throughout the year. And now half the year, this mountain is brown. So I know there is global warming going on. And that's again something that only CFD can help us prevent it. So let's see, how did the CFD as a field develop? So actually, the background of CFD goes back to the early mathematicians in this 18th, 19th century. And they laid 4 critical fields of activity that developed. One was the finite difference method. One was numerical analysis, the matrix theory that went along with it, and there was discovered what was called a Hamiltonian, a minimization principle, that every state, every system has a minimum energy state called the minimization of energy principle, and that is the stable state. Okay, all linear systems have it, non-linears may not. So once people discovered that there was a Hamiltonian, provided you found the minimum energy state, you had a solution. Okay, and that led to the variational method. Richardson is one name you should remember. He is still very handy. The method he developed to test the accuracy of solutions and convergence of them. Then Courant, Friedrichs, Levy, these scientists were the important contributions back in the 1910 and 1920, the early 20th century. So there was no CFD yet, but the basic tools were ready. Now, before the electronic computer came, people started to use the finite difference solution method, and Tom in 1933 developed the flow past a cylinder, and he basically hired a number of poor students, I guess undergraduate students, and paid them like 1 rupee for every 100 calculations or something, maybe 1,000 calculations, and they did a finite difference solution by human hand, human calculators. So all these were done by human calculators. Courant, Tom and Apple, Alan Southwell, these are names which played important role in the history. They were the pioneers. But actual CFD started only with the computers. Frank Harlow and Brian Spalding were the 2 pioneers. So Frank Harlow started in 1950s. He had a 701 computer that he obtained in 1953, I believe. And then Imperial College got in 1963, 64, and Brian Spalding started working on it. The interesting thing was, none of them knew about the other. There were no internet, no emails in those days, and the planes were very expensive to fly. So these 2 people worked, about 5,000-6,000 miles away from each other, with complete, isolation from each other for quite a while. And Spalding is credited with making CFD a common and popular tool. Frank Harlow was at National Weapons Lab, so he could only publish certain things, and all his work was related to nuclear weapons. So though he developed a lot of basic methods, he was not that well known in one. Okay. So let's see what happened next. So here are the two guys. This is Frank Harlow at Los Alamos National Lab, and this is Brian Spalding at Imperial College back in those days. And that CFD emerged at Imperial College in 1960s, and basically a number of developments occurred. Most important was that Brian Spalding developed a common format for flow, heat, and mass transfer. You will see that if you go back to the earlier this century, you'll find that people talk separately of flow. Heat transfer was a completely separate field and completely separate book, and so was mass transfer. So Brian Spalding was one of the first one to see that they were common factors. Then he developed a unified theory for boundary layer jets and wakes, and finally did extensive experiments to pin down the universal constants for the turbulence. So these developments then came very handy. So by the time 1960s came, Suhas Patankar built an integral profile code which was useful for boundary layers. Mika Wolfstein and myself, we started working on the Navier-Stokes equation, the stream function Wojcicki form, which was applicable for 2D and 3D also. So in 1966, we combined our work and we developed the first finite volume code from Imperial College. And then Suhas Patankar, who had gone back to IIT Kanpur, came back again in 1969-70, and he took over and he extended to the velocity pressure form, the primitive equation forms, and developed the simple method with Spalding, which revolutionized CFD. So basically, the foundation of CFD was laid between 1964 and 72 or 70. So we usually say typically the decade of 1965 to 1975. So those are the three people there. The picture that I showed you that is Suhas Patankar, that is Mika Wolfstein, and believe it or not, that is me at those days. So 69 I would attribute, and many other people attribute, the birth of CFD to 1969. Imperial College went out with a post-experience code to which academia and industry were invited. And the first book on CFD was published by Academic Press based on our work, Heat and Mass Transfer in Recirculating Flows, which you typically might know at Gosman et al. Book. That became very popular, and one of the reasons was the book contained the full computer code called ANSWER, which is what we use today still, which was widely distributed. In those days, we gave the code away freely, and fortunately, the same days are coming now. You can now again get free code. So Spalding had a very strict rule that all the publications carried their names in alphabetic order, and that is why the book is known as Gosman, Pohn, Runchal, Spalding, and Wolfstein. Poor Wolfstein, who did much of the work, is stuck at the end, and Gosman, who did very little except compile the book, is stuck in the beginning. But that's the way it works. Now, one thing you will hear about is the finite element method versus the finite volume method. There really is no versus today. Both have kind of learned from each other and borrowed from each other. But basically, we had extensive discussions with Argyris, who is this person, who was at Imperial College, and Zienkiewicz, who was at Swansea. These two people were working on finite elements, their background was solids. They started working with solids and moved to fluids. We started working with fluids and moved to solids, so reverse journey. And for fluids, for nonlinear flow, there is no Hamiltonian. So strictly speaking, the classical finite element method does not work because there is no minimum state of energy. But you can fool the system through variational principles, which in those days was not very easy for high Reynolds number. Even today, bulk of the commercial codes use finite volume approach. There are a few that use finite element approach, but none of them would do. For example, combustion is practically all finite volume codes. Okay. So basically, the name CFD was coined neither by Harlow nor by Spaulding, nor by any one of us, but by a guy named Pat Roche, who published the first book, which was called Computational Fluid Dynamics, 1972. And the CFD of the Imperial College was developed as the engineering tool from the first case. CFD at Los Alamos was developed as a tool to design nuclear weapons. Okay. The Imperial College worked strictly with industry, and our focus was on solving practical problems. So that is why I think this approach became the more popular and more versatile, because the focus was on solving various problems for a long time. And the main difference, and I'll come to that, in the finite volume approach is that it is based upon the physics and not the mathematics. Mathematics plays a very small role. Much of the development of physics, actually, you can develop the finite volume equation without any mathematics at all. Okay, so that's why it is. Okay, so now I'm going to get into the essence of the CFD, and I'm not going to show you too many equations, but I'm going to show you how simple CFD is when you use the finite volume approach. So far, so good. Everybody's awake there?
Yes. Yes.
Huh? Okay.
Yes.
Not too boring. I haven't put anybody to sleep yet, have I?
No, it's very interesting.
Okay. So here is all the CFD you need to learn. Okay. So pay attention to these 2-3 slides here. Basically, what is CFD? CFD is nothing but taking a control volume and making sure what is in it, what goes in, what goes out, and what do you have. So if you take this control volume, okay, it doesn't have to be regular or rectangular or whatever, okay, any control volume, it doesn't matter what boundaries it has to have boundaries, it has to have a volume. Rate of accumulation in this volume, in other words, whatever you put in this volume, increases or decreases, depends upon how much you put through the surfaces. This is the net influx through the surface, right? Okay, how can, let's say this is a granary, I have rice in it. How can the amount of rice go up or down? One, I open a door, I bring some more bags. That is influx. Or I open a door and take some bags out. That is efflux. Okay, what's the other way? Other way is that I grow the rice in there. Okay, that this is a big field and start growing rice in there. Or that the rice, there are a lot of mice there and start eating the rice. That's all there is. Okay, once you realize this, that basically the rate of accumulation is what goes in and out through a surface, or what is generated inside or dissipated inside. That's it. So, you know, I know there are some teachers there, but there are some students that to them I said, don't believe your teacher when they say CFD is very difficult, it's very complex. You know that the teachers have to earn their salaries, so they have to be doing something, so they do that, right? I'll show you that if you can manage your bank balance, you can do CFD. Look at the simplest. Okay, here is CFD. Go back to this one. This statement, rate of accumulation, net influx, rate of generation. Okay? So here it is. If I have a property phi, how does it change with time? Okay, that means growing or decaying, right? This is the amount of rice. Okay, or rather, let's take this amount of money in your bank. Okay, phi is the number of rupees you have in your bank. So d phi dt is the change in the bank, and this is the total volume of your bank. How many bank accounts you have, you multiply by all of them. Okay. So this is, if you integrate over all your accounts, this will be the amount of money that will increase or decrease. Now, how did the money come into your bank account? It comes in through your salary, which you deposit through a check, which comes in from outside and comes into the bank. That's the boundary between the bank and the outer world. Or you have some expenses and you write a check and the check goes out. That's efflux. So that is the money that comes in or money that goes out. That is this term, influx. And this is your amount sitting there earns interest, or you have an investment and you make money on it, or you have a bad investment and you lose, or the bank charges you fees. Okay? So your bank balance, change in the bank balance is the net money coming in and the net interest or bank fees. That's all. So you can basically do this for any volume, independent of shapes, independent of how many sections it has or how you divide it. Okay, this is all there is, and you use what is called a Gauss theorem. And Gauss theorem tells you that as you go to a very small volume, you can drop this delta V and delta S and that, and this term becomes this term. Okay, so that is the sum total of the mathematics that you need. You don't need any math more than that. Okay. Now, if you are to use a finite element method, you will need a lot more math now, because after that you will need to do things like what is a relation between the two different points, and you will have to have a functional and things of that nature. Okay. So one of the things that Imperial College approach did, and we were the first to do it, was that we said, I don't care if it is heat transfer, fluid flow, mass transfer, all this can be expressed as a general transport equation, which is this one. Okay, which is basically just the same equation as this one. I've just written it with nonlinear and other terms. Okay, you can follow this through any book. Alpha could be the density, or it could be something else. So all this, but basically phi is the transported property. This is accumulation called storage. This term is called advection. Diffusion is a very specific process to molecular or to uncertain turbulent processes, and diffusion dispersion that occurs in there. This is a source and this is a sink. Okay, so the G term, the generation term, has been split into a source and a sink. Otherwise, the convection term has been turned. The flux term has been split into convective and diffusive fluxes. That's all. Okay. So this equation is the most powerful balance property that comes for what we call the second order transport processes. It can express fluid flow, heat transfer, mass transfer, electrons, astronomical bodies if they are large enough, provided there is a continuum. And when we have stars in a galaxy, there are millions of them, billions of them. So they behave like molecules of fluid. If you have a lot of cars, they behave like continuum. For example, a stoplight comes, cars come and stop at the light. That's like a compression wave. The light turns green, car starts slowly, and so the traffic problems have been solved by CFD. Okay? Humans, large number of humans, crowd of humans, behaves like crowd of particles. Okay? Fishes, anything that is large enough numbers to be considered a continuum can be modeled by this one single equation. Okay, other processes may come in, this may become complex, this may become complex, but basically that's all there to it. So this is the last equation I'm going to show you. I'm going to go to the application. Okay, Professor Alam, is it better to take a break if there are any questions about this, or should I go on with the application?
We should go on with applications.
Okay. Okay. I'm not going to go into depth in applications. I want to show you the power of the CFD and how versatile it is. Okay. So I'm going to touch upon a number of different fields, and this is by no means exhaustive, but I hope some of these are unusual for you. So first series of application is the environment and disaster management, and that means that we are dealing with earth and atmosphere, air, surface and groundwater flow, earth, plate tectonics. How does disaster management come into it? Well, tsunamis are disastrous, hurricanes are disastrous, plate tectonics is disastrous, and believe me, plate tectonics is basically nothing but a bunch of plastic plates flowing on top of magma, which is liquid. Okay, and the same approaches are used to model it as you'll model any other fluid dynamic problems. Okay, so all these can be modeled with that. So what are the challenges? The challenges in this field are that the uncertain domain of influence. For example, take air quality in Delhi. Okay, I don't know how populated, polluted Aligarh is, but Delhi is pretty polluted, right? And the question is the pollution in Delhi coming only from sources in Delhi? In all probability, no. So when I'm modeling Delhi, what do? Do I go to Meerut, or do I come all the way to Lucknow, or do I go all the way to Punjab, or all the way to Himachal? How far do we go? That is not clear. Okay, what is the region of influence is not clear. So it is an arbitrary decision as to where to put the boundaries, and that creates uncertainties of its own. The second problem is that there is very disparate time and space scales. For example, take the time. You take a tsunami and things can happen in seconds, but the wave that travels around the earth and comes round and round and round might take days. Similarly, take the nuclear waste disposal. That might take decades or thousands of years. Look at the space. Let's say there is air pollution. Well, I'm concerned with what is happening in my building, which is the meter scale. But I'm being impacted by what is happening 1,000 kilometers away in Haryana, where they're burning some rubble in Punjab, and that is impacting my air. So we have to deal with all these scales, and that creates its own problems. Then the other thing is that the nature of the problem is very stochastic. By stochastic, it means very uncertain. Okay, we do not know the initial boundary conditions. We do not know some of the physical inputs. We do not know diffusivity of things, like we talk of the different weather systems, stable weather, unstable weather, things of that nature, which we do not know. So there are a lot of poorly understood mechanisms, how actual smoke is processed by chemistry and then basically settles down or basically converted to something else. These are processes we don't understand. So when you're dealing with this, the uncertainty doesn't come from CFD. The uncertainty comes from the fact that we know a lot of things very poorly. So this is a case where are you seeing something happening there in the screen or no?
The cursor in the video on the left side.
Huh?
Video is on the left side. You have to press the left one.
What do I have to press? This one?
The left side.
Left button.
Bottom
Yeah.
to play.
Ah, okay. Oh, I didn't know that on this one. Okay. So what is going to happen is this is the coastline of Monaco city, you know, and there's a tsunami coming in. This is the water height. Okay, tsunami has a height. You see it hitting this coast first. This is the harbor, which is safe, and you see the tsunami, successive waves coming in and hitting that. So I'll show you the next example will make it clear as to how we can actually visualize it. Okay, so you see all the processes that occur during this one. Okay, so this is how you know, this is one simulation of tsunami. I'm going to show, next one is a little more interesting. And okay, where does this start?
Again, yes.
Okay, so you see now the water coming in. What we did here was, this is the can one, and we actually took the actual coastline. You see the water wave come in? So now you will see which buildings are inundated, which roads are inundated, and so this is actually a virtual reality 3D of actual city. This is the actual city being visualized. So we could do this for Bombay tomorrow. We could do this for Kalpakam. Okay? So you see the water coming in successfully. Look here. The next one will become a little clear. You'll see the water coming in here and inundating all this area. there the wave comes. Okay, so you can see how far it went. You can even see how high it went. All those things can be seen through a visualization, and this is basically nothing but the actual CFD calculation, which is superimposed on the actual layout of a city of Cannes. Okay, see everything become except this one. So this is a safe building. You should have climbed on top of that when the tsunami comes. Okay, of course we did not do the failure of the buildings in this simulation, but some of these buildings may not survive. Okay, so now you see another view parallel to the coast. Look at how the wave came. Okay, this is the main road that goes with the one. It's called, yeah, good go. See, so it's possible. So this much power we have today that we can actually go to the decision makers and say, okay, which part of the country are you worried about? We can actually simulate and tell you what would happen, and that is what's happening today in the US and in many other advanced countries where extensive simulations are being done by the Federal Disaster Management Agency to control these floods. Okay, here you'll see which level of the building is going to be inundated. You see their first level was completely inundated. Okay, and this is the coastline of India, and this was the 2004 tsunami. Oops, what happened here? We need to upgrade in the presentation. Would you also like to? I don't know what's going on here. Huh? Okay, there we go. So this is a tsunami that occurred there, 2004. It's going to hit the Indian coast. There you saw, and Kalpakam was the issue for Bach. So we were studying specifically around what was going on happening in Kalpakam, and the tsunami then turns around, and even the effects, small effects, were felt only a few inches up up to Bombay. So you can see how much coast was impacted and how it was. But here at Kalpakam, there was a significant impact of the tsunami. Okay, let's move to a different field. Now this has to do with the pollution. In coastal areas, many times the municipalities, they take the waste that they have, the sewage and other waste, and they put it through certain channels or other things into the ocean. So this shows the impact of how that goes. Typically, the coastline along the coast, the tides are diurnal. Okay, so the current moves up and then moves down every 12 hours, 12 and a half hours or so. So this was the simulation that you can do, that we did of this. Yeah, this is the simulation from the previous 12 hours. So you see that is coming back, and this is the new coastline, and then the tide reverses, and everything goes back up, and then of course next time it's going to come down again. Okay. Again. So what went in 12 hours away would be coming from this side, and what you want to find out is that none of what comes back to the coast, which is where people are swimming. Okay, so that's how the design is done, that it doesn't impact the coast. So this is a application from the environment and health area. We wanted to develop, we're part of a study to develop a forecast system for allergies. People who suffer from allergies, the allergens in the air and how they impact you. It's a very multidisciplinary study. It involves a lot of different fields which are here. So we use a lot of satellite data, a lot of geographic data, a lot of human-based data, and all that combined into one. This was done for a drug company. And so here, I'm having problem with my videos. I don't know why it's not showing it. Okay, it came now. Okay, so here is we're showing these are sources for allergens up there, and those allergens are moving. This is France, Italy, and part of Spain. So this is a very large field. This must be about more than 1,000 kilometers here. Okay. This is where. This is the wind field on the other side. This is an application for groundwater pollution. Somebody is drilling a well and putting some contaminant into it. Some people are drinking their water and they take their water from this place. Another farm uses this water for irrigation. So does this plume get there and does it pollute these or not? That was the question. So then we did the study over a period of time. This is April 2nd, about 3 months later. And then you see that the plume is reached the first place. And then another one, but it never really went to the second one. Okay, in August 6th, it begins to dissipate. Okay, so these are the kind of things that games you can play. Let me take some examples from the human body, which is 2/3 fluid and rest is deforming plastic, as I said. So here challenges are that the physics and chemistry of the human body is very poorly understood. Blood is near Newtonian, but strong non-Newtonian components. And how does the blood-brain barrier work? Nobody really knows. It's a 4D working space in the sense that the boundaries of the bodies change with time and space. On a short time scale, for example, your heart veins are dilating and pulsating. So you don't have a fixed space in which the blood flows. The blood is flowing and things are expanding, capillaries are expanding or contracting. Not capillaries, the main veins, and then of course capillaries are impacted too. Okay, so there are a lot of unknown mechanism processes so we need to understand. But here is a very interesting problem. There is a problem called hyphema, which is basically accumulation of blood particles in certain parts of an eye. Okay, so particles released from the surface get deposited on the bottom of the anterior chamber, and then the red blood corpuscles, which are 7 micron diameter, they basically settle down there and start creating problems. Particle release from them, they all create a problem. Okay, so this kind of problem was studied with a computational model. Very complex model was made of the whole listen retina and all those similar. This is mainly all fluid. This is the lens, and this is the rest of the structure. Okay, and then okay, all right. So you can do simulation and compliance as to what's going on. This is the case of an embedded eye. Okay, so here we had, okay, I think I'm going to skip that one. Let me go to the drug infusion of the brain. And here this is a mouse brain, and a drug was injected into it to see how fast it diffuses. Then the poor mouse, of course, was sacrificed. And then there's a paper on this by Peter Hart from Virginia Tech, who did the actual experiment and using our code. And they matched the two, and so that kind of work is being done today. Many other that kind. This is another view, the same drug diffusion, little better view of how the drugs are diffusing in the brain. And you can do this drug diffusion anywhere in the body. Let's look at some non-reactive. This is a car. No car is designed today without a body first being analyzed through CFD to minimize, or maximize whatever you're trying to do, to minimize usually the losses and maximize the efficiency and comfort level. Inside the body, inside the car, we can check comfort levels, temperature, anywhere. So those are some applications. This is the case of a wind turbine. Can you see it moving there?
Yes.
Yeah. So this is the wind turbine. Yeah, this is taking. I think Dr. Alam, that day it worked automatically, right? I don't know why I have to doing this. Maybe in free conference, I think.
So if you will play this as a presentation, then it will work fine.
I see. Okay. So you can see how, for example, here, look at how you can visualize where the loss, for example, here there's a high pressure area. Okay, this is high pressure area generated here, and then there are low pressure areas behind this, right? And we can see that there'll be most of the losses are occurring here. So this hub can be perhaps better designed to minimize these losses. And this is the case of there are 4 blades here, fan blades. This is a GIF, which again I think I don't know how to do that. I'm going to move on. This is the application of a coal gas recovery pressure from 1 or 2 horizontal wells, and the question was, how do we recover methane from a underground coal seam, okay, coal mine? And that's a very important problem because methane both is a resource today and we can use it, and also it's very dangerous if we leave it there because it can explode. Simple application for astronomy. As I said, when you have millions of stars, they behave like CFD. There's no electronics today. Example for electronics. This is a very interesting flow. It's a horseshoe vortex and carbon vortex interaction. This is a half cylinder, and you can see the interesting flow which is generated, okay, at different cases. And I think there is a shedding vortex from this, which I hope it is. And you can see that the vortex is being shed behind that, okay? And we can study that today with CFD. This is another simulation of a noise from a cylinder. The noise behind a cylinder can be studied with CFD. This is the application from a fracture network. I think I'm going to skip to the reactive flow. I'm running out of time. I think we have 45 minutes left, I think. So I want to leave some question time. So over 80% of energy today is still being generated by combustion or chemical reactions. Okay, it's supposed to go down to 70-some% by 2040, but for the moment, I think this is what the fact is, that we still rely on reactive flow and combustion for our energy needs. So what is combustion? It's an interplay of chemistry and fluid dynamics, and in the process a lot of heat is released, and to control that heat, chemical kinetics and turbulence play very important roles. Okay. So what happens in combustion is that chemical reactions that lead to the formation of new chemical species, large amount of heat is released, and heat in turn results in large, often explosive increases in pressure and temperature, and these changes cause large changes in fluid density, and then these are harnessed to retrieve that energy. So basically the conceptual basis of computational combustion dynamics is combination of mass conservation and second law of motion or equation, which is the continuity equation, and this is the momentum or Navier-Stokes equations. We combine them with the thermodynamics, first law of thermodynamics, thermal energy, and then species transport, and then of course equation of state and all that. So basically first part is CFD, the first two is CFD, the rest is combustion dynamics. So again, the challenges are that the chemistry is very poorly understood. A reaction between H2 and O2 can be expressed as a single step or as a 50 or more reactions. Actually, I think I've seen 500 step reaction between H2 plus O2, because H dissociates into H plus H, O to O plus O, then OH, and O, all those things form. So they're very poorly understood, and chemistry turbulence reaction is very poorly understood. So if anybody is ambitious enough, is good, and has a strong mathematical background and physics background, this is a very interesting area for research. And then there are integral differential processes that happen, smoke, particulates, radiation, which are not easy to deal with. I'm going to show you a exhaust vent. Here what we had was a fire in a warehouse, which resulting from a leakage in a methane gas. The question was it deliberate? Was it accidental? Was it sabotage? So you'll see that this is these are the places where the gas would come out, and it'll first go up because methane is very light, and then it'll sink down and it will become red, which means that it is at the combustion level. So here you see the vent breaking, and you see the gas spreading up, near the roof because it's very light. Methane is much lighter than air. And now after the top is full, and all this which is red means that it can combust. The smallest spark would combust it. Okay. So this way we can study what's going on, and we can play different scenarios. If it was an accident, what would happen? If it was a sabotage, what would happen, and all those kind of things. This is the case of another case where it's a preparedness for a disaster, you might say, or emergency. This is a multi-level tunnel, one of the most used in Paris, called A86 tunnel in Paris. It's a 5-level tunnel. You know, there are different levels and different 5 parts to it. And one of the trucks is supposed to be in the middle somewhere and then explode. Okay, this red thing is the truck that will explode and catch fire. So whether it was deliberate or accident or whatever. So the question is, what should we do? How should we evacuate people? What is the most dangerous part? So you see the smoke spreading. Okay, you see this here, changes occurring. Okay, with time, spreading both ways. Okay, and one can therefore see which are the safe area. You can see this appearing here. Okay, this part here. If you look in the upper one, you see this going up and down and going there and then coming up this way. That's what those are. Okay, so these 2 tunnels are the most impacted, and the third one here. Okay, this tunnel is not impacted at all, and this part is not impacted at all. So this helps us guide in our preparations for disasters. Okay. This same cross section, it's a different cross section, and it's a little clearer in this cross section. You can see what happened in the cross sectional one. You can see the contours of CO. I think these are CO contours, which is most of the people die from smoke and CO rather than from the fire actually. This is perhaps the most complex machine designed by humans. It's a jet engine, and this is like the M88, which is a fighter jet. And this part is the afterburner. There's a turbine sitting here. There's a combustor sitting here. There's a compressor sitting here. And this is the intake nacelle and all that that's taking the air in. Okay, the air comes in here, is compressed, is put into some is bypassed, some goes into the combustor, which is sitting here. This is the combustor, this little part. And this is the combustor. You can see how this bypassed air comes in to cool and to mix the things and to have a good efficient combustion. That's why you have this bypass air. Then you put more in to recover some energy. You inject more bypass air. So this is very much like the standard design that used to be in the old days. This is what India was trying to design, a design very similar to this one, which is a classical gas turbine design. So this shows different contours. This shows the flow speed, the flow surface, flow vectors, and all those, the total pressure and all those contours. Wood particle burner. This is an example. I don't know if it will work. I've taken it from YouTube to show you the simulation of a internal combustion engine, which is another complex machine designed by humans. Okay, this is courtesy of RFA, to RFA, and it uses the ICE program. How do we go back to that? Okay. This is a high-speed civil transport, Mach number 2.4, visualization of the wing and fuselage at this one, the energy level. This is the supersonic aircraft. This is the rocket. This is a NASA simulations of rockets shuttle, and you can see the shuttle with the 2. Actually, I think there are 4. I think. Or is it 2 in this case? In this case, I think they seem to be, they seem to be only 2 booster rockets. Okay, this is the boosters that ignite in the first stages and separate, and then the rocket goes on and ignites by itself, its own fuel. This is perhaps the most ambitious project today, which is a hypersonic scramjet. It's supposed to go from anywhere from 10 to 30 Mach, which will be the, which you will arrive, you leave in the morning and arrive at before the morning starts in another place. And it's an integrated design with aircraft, and everything is in engine, aircraft, everything is one design, fuselage. There's no, there's no separate parts to it. This is a ramjet, and let me come to the last part, which is the next stage in the evolution of CFD tools. It's a very simple perspective, and let me give it to you what I think would happen. So the CFD of the future, as we know the CFD codes today, I think they will disappear from the engineering practice. Why? You take any code that you're using today, I don't care which one it is, you'll find it's too cumbersome to use. Even after using it for 5 weeks, 6 weeks, you keep making mistakes. It's a long training period. There are no checks and balances to reality. People find solutions which make no sense. They are, do you say, oh, my program blew up? And you look at the results and make no sense. Okay, so there are no checks and balances because the physics is not being strictly adhered to. The second law of thermodynamics is being violated. Okay, quite often all the laws are violated. Okay, so there's a poor overall reliability for critical application. If there is a critical application today, the best CFD practitioner will not be confident to design an engine, build it, and fly on it. Okay, he will not risk his life on it. He'll say, no, let's first test it somewhere else. Okay, that is not where we want to be. We want to get expert systems, and the expert system will not be CFD system. CFD algorithm would be one part. Like take your refrigerator today. It perhaps has a number of fractional horsepower motors in it. One runs the fans, one runs the cooler, one runs the fridge, one runs, ice machine, but we don't see them. Similarly, for example, we were part of designing a refrigerator where we had an embedded CFD tool in it, which will automatically monitor the temperature in different places, and as you put one more carton of milk, it will begin to chill because it knows the temperature has risen. Or if you put it from the first to the second shelf, it will automatically shut off the first shelf and start cooling the second shelf. Okay, so that's what I call an expert and system, which has a built-in intelligence. So tomorrow's CFD application will be specific to different problems, that you will not use the same CFD code to design an aircraft engine that you will use to design, let's say, environmental problem. Okay, that those days would be gone very soon, and you would have significant artificial intelligence built in, and there'll be application-specific machine learning. And finally, you will have virtual reality tools in which, just like what I showed you, one analysis, but there's something much more powerful than that, where you can actually walk into an engine, imaginary, right? Of course, it's imaginary, it's an engine in a computer. You can walk in and you can see, oh, there is a little bit of problem there, there's a high pressure area there. And you can say, okay, let's change this injection so much to solve that problem. Okay, so that is what would happen with CFD tomorrow, and there are already virtual reality systems, like NASA is working on a virtual reality system where you can visualize a whole engine, and you can simulate a whole engine, and you can move inside the engine. You can say, let's look from this point, let's look from that point, let's look down, let's look up, and it'll show you what's going on toward the engine. So that is what we want to do, and that is where we want to be tomorrow. Okay, I think I hope you guys are still awake, and I thought I'll allow enough time for discussions and not bore you too much of my talking. Okay, thank you very much, and I look forward to seeing what you like to do now. I think Professor Alam, you should take over and tell me we have sometime if you like to discuss things. I think we still have 15-20 minutes, right?
Yes. Sir, let me introduce.
Any questions?
Hello. Sir, let me introduce me. I am also one of the organizers of this workshop, and I haven't met you before, but so I also happen to work in the CFD area. So I was interested in your tsunami calculations, which you showed. I wanted to just know that in the tsunami calculations, are you taking the Indian Ocean kind of a depth? What you can?
Sorry, firstly I missed who's speaking.
The bed, who's the bed, and do you? Who's speaking? This is Professor Anwar.
Sorry. Sorry.
Anwar.
Anwarji. And I'm sorry, the voice, it's coming a little broken up. So I missed the main point. You said, have we taken care of Indian Ocean what? Bathymetry?
The bed, topography, yes.
Topography?
The Indian Ocean topography of the bed.
Do I understand correctly that your question is that did we take into account the actual topography of the Indian Ocean?
Yeah, exactly, sir.
Okay. Yes, we did to the best of the ability. I think we relied upon firstly the data supplied by Bach Atomic, and they have taken extensive simulations, and then also I believe that we used the navigation charts to refine the near coastal bathymetry, and then the bathymetry of course also comes from the Indian Ocean. What's that Indian Ocean? I forget the name of the organization. I think it's National Oceanographic Association, something like that.
Yes.
They have an office in Goa also, I believe.
Yes, exactly.
Yeah, so I think the bathymetry charts, and then of course there is the British Admiralty charts, which are very useful, and Indian charts are basically in the deeper ocean are basically dependent upon the British British Admiralty charts. So yes, a number of sources were identified, and there was a lot of data. I think you can request Bach if you're interested in that problem, and they would be able to supply you with the data.
So just the second thing related to that. So normally in geophysical fluid dynamics of these oceans,
Professor Alam, is it possible to speak without some kind of echo? I think वो openly बोल रहे हैं ना, तो अगर mic में वो हो ना silence हो जाए तो मेरे ख्याल echo आ रही है.
So you are able to hear me now, sir?
Much better.
Okay, sir. So I just wanted to ask another question related to this. The simulations which I have seen that people take, so they don't take no slip in the topography of the bed. So you have taken no slip, or you have taken the slip velocity. So that is the second question I wanted to ask.
No, we go with in the vertical simulation, there were two kind of simulations done, They were, the oceanographic is done by typically two kind of simulation. One is a vertically averaged, vertically integrated simulation, right? Okay. The second is when you're doing a full three-dimensional one,
Yes, sir.
Okay, so when you're doing the vertically average, then basically there is a slip velocity in the sense that you're taking a vertical average, And then people sometimes would take the extra friction at the bottom and assume there is a log law or some kind of power law. That is what's done in those cases. So the friction is computed, the bottom friction is computed from a power law. Now when you're doing a 3D one, then you have to take a no slip at the bottom because to satisfy the kinetics, you need that. Okay,
Yeah,
so because
exactly.
a log law, if the turbulence velocity or log law or something like that we form, depending on how it is. Okay.
Yes, sir. So I have seen
So it
some
depends on the
simulations,
approach.
some papers who have used two-dimensional, who have modeled this flow as a two-dimensional flow, and then they put on the bed they were putting slip velocities for this topography, and they will put slip whatever. So probably because they were doing in 2 dimensions, so therefore they use the slip kind of a thing over there.
Yes, they would then, because they would assume that there is some kind of a log or a power law profile.
Exactly.
And below that, and then they'll use the effective height of that. Yes.
Yes. Thank you, sir.
Yeah. Thank you.
Anybody else wants to ask questions?
I'm sorry.
Good afternoon, sir.
Good afternoon.
Yeah, I am Adnan Hafiz here, faculty in this college.
Hanji.
My question is, sir, you talked about this embedded CFD algorithm in the refrigerator.
Right.
So where do you embed that, in the sensor or in the PCB of the IC?
There is a dynamic system that is put in. Okay.
Yes, sir.
And
yes.
What happens is that the different loads are pre-simulated in this particular case. I think one day what you're saying would happen, but
yeah.
at the level that we were, we
yes,
basically simulated a large number of static scenarios.
Yes, sir.
And coded a response based on those scenarios.
Okay.
So they were sensors.
Yeah.
So they were sensors which
yeah.
would, based upon that, would do a lookup table and say, okay, do this. Okay, so there was not a dynamic CFD calculation once the fridge is manufactured. Okay.
Okay, sir. So there is a feedback system.
There's a
feedback control loop must be there.
Well, imagine this way. Let's say you want to see what the comfort level in a car would be based on the number of people. ठीक है? तो आप ऐसे करोगे कि आप पहले कार को सिमुलेट करोगे 4 आदमियों से, देखो कितना एयर कंडीशनिंग होना चाहिए, फिर 2 के साथ करोगे, फिर 3 के साथ करोगे, फिर समर का करोगे, विंटर का करोगे, so you'll have a table, ठीक है ना?
Yes, sir. Thank you.
Based on that table, you will then design the car. So the CFD goes up front. But I think you are absolutely right. Tomorrow's system, that is what I am talking about, tomorrow's system would actually have a little calculator, CFD calculator built into the refrigerator. Okay?
Okay, thank you, sir.
It will be a chip or it will be something else.
Okay, thank you, sir.
Thank you. You're welcome.
Sir, I have one question for you. You were basically talking about incorporating machine learning into the CFD. So basically, we compare turbulence modeling coming through various turbulence models used in the CFD, and then using machine learning in order to do the same prediction. So how do the predictions match up, and what else can be done in order to further refine them? Because you need a high number of CFD simulations to be done before the machine is able to learn the model.
That is absolutely correct. कौन सा बोल रहे हैं? Hello.
My name is Professor Beg.
Professor Beg. अच्छा. Professor Beg, it's not, obviously I can't give you an answer. You know, making a prediction about the future is very, very uncertain. But I think what is going on right now is that you're basically, it's a combination of, you might say, something like a neural network at this stage and a typical CFD algorithm, right? So you're absolutely right that since we do not understand turbulence and a number of other uncertainties, so the machine would have to learn by itself. But how I see it going is that you would first do some simulation. Let's say we want to control design of an aircraft engine, right? And you're saying I need a certain thrust. And then you find out that the current system that you have, which is reliable, generates certain amount of thrust, right? So you will have that information built in. You will do a number of simulations where you will change, let's say, the fuel ratio, a little fuel air ratio. and you will see what happens to the thrust. And the system would begin to learn from those, and then after a while it makes up its own kind of, background information saying, if I do this, then this happens. If I do this, then this happens. If I do this, then this happens. Then it will begin to predict the max one, and then say, okay, the objective function is maintaining the thrust, and constraints are efficiency and safety and whatever it is those constraints are. So I would think that the first stage would go like that. But I have seen some very beginning kind of work where people have basically just thrown a system, given up some basic heuristic rules about how fluids behave, and let it evolve into simple kind of solutions. So that is also happening. So I think more than that I won't know, I won't presume to know.
Okay. So there's another question. You are talking about basically CFD heading into the direction where you'll have different codes in order to solve different problems. So basically you are moving away from the idea of universality, though in physics basically we are moving towards theory of everything, grand unified theory. And here you're talking of going into disparate codes for solving different problems. So why is that so?
Well, first we already have theory of everything. We know that that at the continuum level, Navier-Stokes equations are there, and at the particulate level, non-quantum particulate level, Boltzmann equations are there. Okay, so we already have a theory which is much more comprehensive for the material world, right? Okay, yeah. So if you look at it, so the question is, let's say you're designing an aircraft engine. Let's say today you use, I don't know what code you use, OpenFOAM or ANSYS. Let's say you are using it to design an aircraft engine, right? Okay. Now, then you use the same code, for example, to design a car, right? Two very complex applications, right? Okay. Now, what happens? Look at the process that happens. The geometry of the car engine is reciprocating engine very different than the geometry of a aircraft engine, right? Okay. Yeah. Now, same code has to do with both, right? Okay.
Right.
Obviously, the code can't be as efficient as it could be if it specifically dealt with one or the other, right? Because you have to allow for reciprocating in the same code. You have to allow for the modules that do the reciprocating part, the modules that inject in a certain way, modules are right. Okay. Now the second thing is that today's code, you take any code, you take OpenFOAM, you code NC, you design an aircraft engine, and you give it to one of your students. You come back and you look at the solution. This solution makes no sense, right? The temperature is blown up. You made some mistake. Go back and check it. Now tell me, shouldn't it be the job of the code to find out that the solution doesn't behave physically? Wouldn't you like a system where the solution says this solution is wrong or would not give you that solution? For example, you can take ANSYS today and you can tell it that the viscosity of water is 0, okay, which is not reality, okay. So there are no limits, independent limits to check either the input veracity or the output veracity. And therefore, it's very expensive. Let me give you one example. To do a typical simulation today of an engine, the companies are spending millions of dollars to do a typical engine simulation. Human beings are being charged in the US at, I don't know what, $100 an hour. Okay, in India they will put 5,000 rupees or whatever it is. Okay, a very expensive process, and you have a student sitting there for 6 months doing nothing else but doing one simple problem. Okay, if it was a specific application, most of it could be automated. Okay, if it was just a aircraft engine I had to do, I know I could develop a dedicated processor that will generate the grid for the aircraft engine. The trouble is that I'm today asked to have a grid generator that can do the aircraft engine, it can do the environment, it can do this, it can do that, right? Okay, so so I think they're just not viable. And the other thing is that CFD is very slow. You see, I give you one very simple example. I started in 60s, and my CFD code was perhaps, say, I don't know, maybe about 500 statements. That was all that the CFD required. Okay. Today I find that 90% of our code of answer has nothing to do with CFD. It's input, output, geometry, contours, gridding, things of that nature. Okay. So CFD is embedded already. So I think what would happen down the line is that it's much more efficient for, as an engineer, if my job as a General Electric to design an engine, my job is not to learn CFD, my job is to design an engine. I want to be there. I want a tool that designs an engine for me. So that's at least, I think, where I see it going. And you already see that. You are already seeing specific application tools coming up. You see all kind of special application tools coming up which have become standard in the industry.
There's another question of mine. Basically, we have been solving partial differential equations in order to understand the mathematical nature of the problem. Instead of PDs, do you envisage in the future we'll have some sort of nonlinear algebraic equations which we can solve in order to get the same physics out of it, something on the lines of automata theory?
I think there's already some automata-based work going on with the CFD. There are simple rules for molecular interactions. The problem is that the computers are not powerful enough to give us anything meaningful at that stage yet. So I think if it could happen, after all, the actual basic interaction is very simple. Two molecules interact, and what they do, based upon some physical ones. The question is that to do the automata kind of approach, the problem is the n-square problem, and we need lot of interactions defined, especially the integral properties like pressure and others, which in fact, which move much faster. I think there's a disparity here in the time scale because pressure interacts. It's an elliptical phenomena. It interacts very fast, and so I think those cannot be solved effectively with automata today. I think the pure kinetic problem can be done with automata. So I think you are going to need some kind of an integral method for the moment.
Good day, sir.
Raji.
Sir, I am Nafis Ahmed, undergraduate student from Zakir Hussain College of Engineering and Technology. Sir, I have a question that you showed the simulation of the tsunami. So I want to ask you that the tsunami, the effect of tsunami that is created from the waves, and waves have connection between originated from the connection of the earth to the sun. So in the summer, the earth is closest to the sun, and in the winter, the earth goes off from the sun. So the interaction of the wave, the impact of the wave must be different in the different season throughout the year. So you showed the simulation. Are you implement the effect of the interaction of sun or earth or real physical disturbances that can be happen throughout the year? So if you design the buildings or any all the components around the coastal areas, the design may be failed if we design without the implementation of the real situations.
I think we are talking of two different phenomena. Basically the sun doesn't have much role in the oceans. Moon does. And I mean, sun has very little impact, but moon does. And that is the influence on the tides. Okay. Now, the tsunami is typically created when there is a shift in the tectonic plate, and the water level suddenly changes. It's an underwater earthquake essentially. And there are two types, what they call a slip fault or a thrust fault. And then the bottom of the ocean suddenly drops or moves. Okay. Now that creates a tsunami. Okay. So tsunami doesn't have anything to do with the tides. The tidal time is tides typically, as I said, are diurnal in most places on Earth. There are exceptions, and their time scale is 12.5 hours. Okay. Tsunami, on the other hand, moves at a much faster speed. It moves at almost like supersonic speed, because the water wave, it's a deep water wave, that wave moves and it superimposes on the tide. So depending on the state of the tide, yes, the local level would be different. But for all practical purposes, you can consider the two impacts to be independent. In other words, the tides do not interact with the tsunami, and tsunami doesn't interact with the tide. They are simply added to each other. Because the time scale of tsunami interest is usually short, and usually till it gets there. Okay, usually that's what happens. It happens in a few hours. Okay. So the water level, if the water level is already high, the tide was already high, then you would do it. So typically you assume, and I would think that that's about, I don't know what percentage I would put, but I put very high reliability that you can just add the tide level to the tsunami level for the actual water level locally.
Thank you, sir.
Okay, thank you.
I think this diurnal cycle also has a very definite in terms of time, like a sun. So if you embed that in the code already, that can take care by itself.
Yes, the diurnal cycle, you see, typically what happens is that the tidal cycle at most places are very predictable.
Right.
Okay. Of course, there are coastal areas where we do not know, and diffraction occurs and all those things happen. But otherwise, like you take any part of India, Indian coastline, you'll find for each city, you can already get the tide charts, okay? And they're quite reliable, okay? And they're repeated, and they are, most places they are very reliable, okay?
Yeah, so it's just by chance that at what point of time tsunami happens, I mean, the diurnal cycle can be in favor or against both.
Believe me, in most places, it's not going to make a big difference on the Indian coast. You see, Indian coast doesn't have very high tides. It's not like North Sea where the tides are very high. Our tides are typically hongi to 4-5-6 foot hongi, okay, meter, on the meter rate, right?
Right.
And that can be handled by the regular design. But the tsunami, just say, a real tsunami would perhaps have an impact which is much higher, much larger, which is not predicted by the tide.
Hello, sir. Just to add to another thing which I wanted to share with you. So the lab in which I worked before, in my postdoc, they're already doing virtual reality with CFD.
Oh, fantastic.
So ये LIMSI, it's in Paris. It's a laboratory informatique, the mechanic, and more things. So they have a division which is based on computer learning and machine learning, and they have a CFD and fluid mechanics division. And I have really they have started to build the system, and when I went there in 2010 and 11. So that time I experienced the virtual reality with fluid mechanics, not with CFD modeling, but with fluid mechanics. So I can just look into the vortex and feel the vortex around it.
Right. No,
so you have started to build it.
Yeah, no, you're absolutely right. There is a number of places today which have fairly advanced virtual reality. NASA, of course, is one example. In Sweden there is a school also. I forget the name of the school. We interacted with them in the past. In Paris, actually, the virtual reality movie I showed you was also developed in France. It was developed with CNRS. Okay.
Yeah, they have the CNRS laboratory.
Yeah.
This laboratory LIMSI is under CNRS.
Under CNRS. So we also cooperated with CNRS on that one. And they are very good in topography, building topographies, and in virtual reality of the cities and all that, and of the CFD. And there's a number of labs now becoming very active. The problem with virtual reality today is that the tools cannot be easily taken out of the laboratory and put in the desk of engineer.
Yes, sir. Yes.
They are still very specialized and very expensive. You know, a typical virtual reality lab today perhaps has a budget of a few crores annually.
Exactly.
So we need that kind of money. So it's not yet become. It's where computer used to be 50 years ago. You know, हमारे ज़माने में computer was so expensive.
जी सर.
And so I think we need that to come down to the level. But you're right. That I think that is where the real use of CFD as a design tool will be. When I can design a product with CFD and visualize how it will behave right now.
Sir, I completely agree with you that the future would be that you have specific codes which are specific codes for specific jobs with virtual combined with artificial intelligence. Because as you say that the nature of the problem and the nature of the mathematical model to it is always changing with the problem. So it's a kind of if you have in a compressible mode, you have a different kind of issues which you are going to take up. So you design your own code so that you have the most efficient or the better way to solve this that problem.
Well, let me give you a very simple example. You take code like ANSYS or OpenFOAM, right?
Exactly. Yeah.
Now you try to do a porous media problem with OpenFOAM or ANSYS. And they basically putting in terms in Navier-Stokes equation, Brinkman terms and other terms, Brinkman-Forsheimer terms, to try to simulate the porous media flow. Now, actually, a porous media flow has a different set of equations called Darcy equations. Now, why do you want to write a code for Darcy equation which uses geological terms, rock types, and depth of the stratigraphy, permeability, porosity, hydraulic conductivity, right?
Yes, exactly.
Why would you want to combine that code with a Navier-Stokes code which uses viscosity and different approaches, right? Okay, because you'll not do either of the jobs properly. You only make it one complex, right? So we decided a long time ago. For example, we have a answer code for Navier-Stokes equations. For porous media flow, we use a Darcy code called PoreFlow. For air quality application, we use our random code, which is based upon stochastic simulations, which solves random walk problems. For surface water flow, we use a tidal code, which we use shallow water equation. Okay. But if I write one code which can solve Boltzmann equation, Navier-Stokes equations, and I don't know what else, quantum equation, it will not be very efficient. It will not be very appropriate. So I think people just use it, but I personally am not in favor of using generalized codes for every application. I think those days are. You don't do any of those very well. That's what I think.
I think we are coming to an end because the time is about to be over. Where are you located in USA, Dr. Runchal?
Right now I'm located in Los Angeles.
Okay.
But I'm about half the time in India usually. It just so happened that you caught me at a time when I'm here, and then I'm in McLeodganj in Dharamshala.
Very nice. So that's what exactly I wanted to know, that how frequently do you visit India? Because I would like to have you at AMU as soon as possible.
Yeah, I would love to. Actually, I know one of your old I think I have met some of your faculty, but I also know what the connection. I had a connection with AMU, and I think, let me see. आपके एक डायरेक्टर हैं.
So is Mehdi Abbas Rizvi? Professor Mehdi Abbas?
I think Rizvi वो earthquake में है या किस field में है वो?
He was at Imperial College. I don't know. He was your contemporary. He works in combustion.
Rizvi was not. No, I know his work. No, he was not my contemporary there. He came. He's much younger, I think. He's much younger, I think.
You don't look that old.
I'm 75 years.
Oh wow.
Mega Dr. Rizvi is much younger. Kya age है उसकी? I think he's like 50, right?
He is past 75.
Oh, he's past 75?
Yeah.
No, 70.
70, yeah. No, I do remember at Rizvi. I think he's, I think Rizvi was, is it Whitelaw student? Whitelaw था उनका professor? Lockwood, हाँ, Lockwood. ठीक है, Lockwood, yeah, Lockwood का student. You see, Lockwood and I were contemporaries. We were there together. Lockwood had just finished his PhD, and we all finished around that time. So Lockwood का student. So he must have worked on combustion.
The PhD course.
So,
no, I'll love to come. As I said, I usually come to India about 2 months, and then 2 months in the US, and like that. You know, so I come 2 or 3 times, and so I, you know.
Yeah, we would like to have you at AMU at least.
I would love to. It'd be a pleasure.
So yeah, we can be. Just 3 hours.
3-hour drive.
Yes, the road is
there a
good.
Flight also?
Not yet, but soon we might have.
part of the Udan scheme?
Yeah, no, not Udan, but they have promised a new airport coming up somewhere in between New Delhi and Aligarh, so that will cut short the drive time half.
Acha.
Yeah, this is India. We cannot rely on that.
No, I think there are. I mean, I know from Himachal that our airport was. उसके 3 उद्घाटन हुए थे over about 15 years.
That means it must have seen 3 elections.
Well, about 5 elections in between.
That's even more.
हाँ, तो वो तो होते रहते हैं. So
lastly, Dr. Runchal, we have giving a memento to our speakers.
Okay.
The only problem is how to deliver to you.
Oh, you should. Where you can mail it to Dharamshala, or I'll come and collect it when I come next time.
You send me the mailing address and we will try. Or if you want, we can keep it reserved for you, and next time you get 2 mementos.
No, the trouble is I travel very light, और आपके memento कई बार बहुत heavy हो जाते हैं.
No. It's very light, and it's of everyday use. Believe me.
Okay.
So I think the audience are getting impatient to have a cup of tea here.
Sure. I can fully understand, and I do not keep them from the tea. And it's a pleasure, and I'm glad. I was concerned that somewhere in between the connection would go, or internet would go, or electricity would go, and I'm very impressed. That did not happen.
Yeah, things have changed a lot in India.
No, that I know. I was there only 2 months ago, so I know that.
So we also appreciate your time. It must be late over there. And we expect to be in touch and have a long-term relationship with you, at least with the institution.
Sure, you have. I look forward to it. Okay, thank you.
Once again, I thank you very much and I appreciate your time and effort.
Thank you, sir. Thank you.
All right, have a good night.
Bye-bye. Good night, and or good morning to you. And